Alright, this is the notes for section 910, using logarithms to solve exponential equations. If you haven't done so already, make sure you read the section before continuing on with these notes. Now, the first thing I'd like to do is look at different ways that we can solve b to the x equals a, and by solve I mean solve for x. When we started looking at logs, one of the reasons why we did that is because it was an inverse operation to b to the x equals a. So we use logs to kind of help us solve this. But before we did that, there's some things that we were able to do. One was we could solve them in our head. So if we have 3 to the x equals 81, we can ask ourselves the question, well, 3 to what power is equal to 81? And I know that 3 to the 4th is equal to 81, so that's how that would work. Yeah, and we could even solve kind of simple equations like this by in your head. I mean the exponential part in your head. So we could subtract 75 from both sides and get 5 to the y equals 125, and then we could say, okay, well, y 5 to what power is equal to 125, and that would have to be 3. So that was one method that we used. Another method that we looked at was solving them graphically, where we could graph. If I want to solve 5 equals 3 to the x, I can graph y equals 3 to the x, and I can graph y equals 5, and that intersection point, that x value would be the solution that we're looking for. So as you can see, where it intersects is at approximately 1.465. Therefore, we would say that x is approximately equal to 1.46. Okay, and we can. A third method that we could use is we can use the solve feature on our CAS. I could say solve 5 equals 3 to the x for x, and it will give us that value of x as well. Okay. Well, what we want to focus on in this lesson is the fourth method, and that's the idea of using logarithms and our other algebraic skills to solve for x in these situations. Alright, let's take a look at example 1. It says, recall that the formula for interest compounded continuously is a equals p e to the rt. At what rate of interest compounded continuously do you have to invest your money so that it will triple in 20 years? So we're looking to solve for the rate, which is r, and we should have all the other information. So let's plug that information in so that we can solve for that. Now, they didn't give us the exact amount or the exact principal, other than the fact that the amount that we end up with has to be 3 times what we started at. So the easiest way to deal with that is, let's start with a principal of 1 and end with an amount of 3, because we can carry that out no matter what the values are for p and a. So I can say 3 is equal to 1 times e to the r, and then that's raised to the t. Well, t is going to be 20, because we want it to triple in 20 years. Okay? So we're going to try and solve that for r. So I can rewrite that now as 3 equals e to the 20r. So I'm left with solving for r here. So here's where the inverse function comes into play. Since I have e, I'm going to use, for my log piece, I'm going to use the ln. So what I'm going to do is I'm going to take the ln of both sides here. So I have the ln of 3 is equal to the ln of e to the 20r. Okay? Well, e to the 20r, that's like saying 20r times the ln of e. And I know that the let's just write that. The ln of 3 is equal to 20r times the ln of e. And I know the ln of e, that's like saying e to what power is equal to e, so that's going to be 1. So really I have the ln of 3 is equal to 20r. And then to find what r is, I would divide by 20. Therefore, r is equal to the ln of 3 over 20, which now is when I would go to my calculator. When I enter that on my calculator, I have the ln of 3 divided by 20, which comes out to be, if I round it to the nearest thousandth or the nearest tenth of a percent, so that'd be 0.055 roughly. So I've got 0.055. So this would be, in terms of my R value, that would be 5.5%, because we want to know at what rate of interest. So that would, we want to write that as a percent. Here's number 2 then. It says the amount A of radioactivity from a nuclear explosion is estimated to be modeled by A equals A sub 0 e to the negative 2t, where t is the number of days, that's important, since the explosion. How long will it take for the radioactivity to reach 1/1000th of its original intensity? So let's rewrite that equation with the things that we know in there. So if I want the radioactivity to reach 1/1000th of its original amount, I'm going to let its original amount be 1 and let A equal 1/1000th. So I can say 1/1000th is equal to 1 e to the negative 2t. Okay? Well, 1 e to the negative 2t really is just like saying e to the negative 2t, so I can actually get rid of that 1. Now, since I have e involved here, to solve for an exponent, what I'm going to do is I'm going to take, in this case, because of the e, I'm going to take the ln of both sides. Anytime you have a base of e, you're going to use the ln. So if I do that, so I've got this right here. Well, the ln of e to the negative 2t, well, that's like saying e to what power is equal to e to the negative 2t. Therefore, the answer to this is negative 2t. That's why we want to do that, is equal to the ln of 1/1000. So now, if I'm going to solve this for t, I need to divide both sides by negative 2. So I have the ln of 1/1000 divided by negative 2 is equal to t. Okay? So let's go to our calculator and figure out approximately what I can say that t is approximately equal to 3.5. And remember, t is in the number of days, so it'd be 3.5 days approximately that it would take to reach 1/1000th of its original level. Alright, here's example 3. It says solve 5 to the x equals 32, first by taking the common log of each side, and then by taking the natural log of each side. So if I'm going to take the common log of each side, I would say the log of 5 to the x is equal to the log of 32. Well, that's like saying x log of 5 is equal to the log of 32. Then I can divide both sides by the log of 5. This cancels out. So x is equal to the log of 32 divided by the log of 5, which that's when I can go to my calculator then. Let's actually round it to the nearest thousand. So 2.153 would be a good approximation for that value. Now if I take the natural log of each side, it's going to be exactly the same. The ln of 5 to the x equals the ln of 32. I'm going to do the same process, therefore x would be equal to the ln of 32 over the ln of 5. Now let's do that on our calculator as well. So once again, approximately 2.153. So it doesn't matter if I use the common log or the natural log in doing that solving. Okay, I can use either one. I'm going to get the exact same answer.